Welcome back. Let's talk about Lamport signatures. So you've seen this construction in the lecture, and what I want to do is to slightly generalize it and then prove it again. So the whole idea that I want to pursue is that eventually I don't want the messages to be like n bits anymore, but I want to messages with n digits, where a digit may be more than 0 or 1. For example, it may be 0, 1, 2, or 3. For example, then I could have messages that are kind of written in base 4. And this is kind of nice because if I do this, then my signatures essentially become shorter, right? So in every single digit of this message, I can encode more information. So for example, if I did a base 4, I can encode 2 bits per position, per digit in M. And as a result, the signature here will become shorter. So if I do it base 4, for example, and I would still kind of canonically rewrite my bit string to be base 4, then my signature size would be half as much. So that's the goal, have signature scheme for like higher bases than 2. And essentially we can keep almost all of the idea intact. Basically in the original we had n of these columns here, and each column had 2 values, one for each possible bit for this position in M. And now we we add some more rows so that each column has like d, so that each column has d values, one for each possible digit for our new M. So we're not doing this for b equals 0, 1, but we're doing it for b equals 0, 1 up to d. And now the secret key would basically just consist of and then obviously similarly for the public keys. So the public keys are now actually, let's make this d minus 1 so that I can actually talk about base d. Okay, and then verify kind of works verbatim the same. So for each digit in M, we get 1 sigma I in sigma. We run this through the one-way function and we check whether this actually conforms to the public key on the same position. All right, so this is the scheme, and I claim that this is still secure, assuming that f is actually a one-way function. And we'll sketch the proof here. The proof is essentially the same. It doesn't get much more complicated than the original one. And if you just set d to be 2, then you get back your old proof. So we start with an adversary against the signature scheme as usual, and then construct an adversary against the one-way function. So what do we do? A prime gets this f of x as input, and well, it will want to use A. So A prime will play the role of the challenger for A in the signature game. And for this, the first step, of course, is coming up with a public key. Now, the idea is that we kind of try to put our f of x into the public key as one of these yi's in order, and then hope that like the forgery that A makes will include the preimage for f. Because signatures consist of preimages of the public key, so we can kind of hope that ours is among those. So essentially, as in the original proof, we just choose a random position in this public key here, and then we just put our function value in this at this position. And then all the other yi prime b prime, we just compute normally. So we choose a random x ib, and then compute f of x ib. And we'll call these random indices I star, B star. Okay, so then the situation is that for y, I star, B star, we don't know a preimage, and for all of the others, we know them because we computed them normally. Now A has gotten the public key. Now A can ask its one query because it's a one-time signature. Maybe I forgot to mention this. But yeah, we're proving that it's a one-time signature scheme. Now for this query, we can easily answer it. Usually, hopefully, we just need to return the proper pre-images that we computed here. The one thing that's getting in our way is potentially we can't do this, and this would be the case if the pre-image we would have to give to A would be the one that we don't know, namely this X that we got as a challenge here, where we don't know the X. So this is the case, then we have a problem. So this would be kind of our first error case, which is if at the ith star position, m hat has the value, or like the digit b star. So if this happens, we would have to reveal x, because it would ask us for the pre-image for y I star b star, which we don't have. So yeah, that's our first error case. But let's argue what is the probability for this to happen. So what is it? Well, this is not too difficult. This value is 1 over d. This because essentially we chose this b star randomly up here. The view that A gets is independent of I star B star. So what A gets is just a public key where everything is distributed as usual. So A doesn't have any information which B star we chose. So with probability d minus 1 over d, we can just go on. And this is good enough. In the original proof, we had this too, and then the probability was just 1/2. All right, now that A has asked for a signature on M hat, we can essentially give him the pre-images, assuming we didn't have bad luck. And then after we've given that to him, A will hopefully output a signature. And now what we've been hoping for is that this signature, sigma here, actually contains our pre-image. And according to the definition of the signature, this is the case if the digit at the ith position in M is actually the digit that we guessed in the beginning. Because then sigma would contain xi star b star, which is the thing that we're after. So now the question is just how likely is it that we're lucky here? So what is the probability that mi star is equal to b star? Take a second, think about it. So we can't do the analysis from before anymore, like this and this kind of look similar, but now we're at different stages in this experiment. And essentially the thing is that now this value and this value, they can depend arbitrarily. So we can't really say, we can't do the everything is independent argument anymore. However, from the fact that A wins, we can actually get some information about mi star. Namely, we know that m is not equal to m hat, because otherwise A wouldn't win. Okay, so those cases are not interesting to us. But if m is not equal to m hat, then m and m hat need to have at least one digit where they differ. Okay, and that's where our second guessing, or like our second guess comes in, where we chose this I star randomly. Essentially, this is our guess that m and m hat will differ at position I star. There's at least one position where they differ, so the probability that we hit this is 1 over n. Obviously, there can be even more indices that are different, but at least we have this probability. because if we guess this at least one index right, then we will have different digit at I star position. All right, so this is something. So with probability at least 1 over n, mi star is at least not the same as mi star hat. So what is now the probability that actually mi star is equal to b star? So if we're at this stage, then this didn't happen, right? So mi star hat is not b star. And mi star is not the same as mi star hat. So what can mi star still be? It could be any digit, except that it can't be mi star hat. And this mi star hat, the one digit that it cannot be, that digit is not b star. So there's one digit that we can rule out, which is mi star hat. And this digit that we're ruling out is not b star. So for mi star, there are still d minus 1 possible choices. Every possible choice except for mi star hat. Because the adversary has no information about b star, the chances that b star is actually the one that's chosen among those d minus 1 left choices is 1 over d minus 1. Assuming that we're in the scenario where already this happened and this happened, so the adversary wins and we guessed the index correctly, that where the digits differ. So overall, we can write this as being at least 1 over n. So we need to be lucky with guessing the I. And then if we were lucky with guessing the I, we again need to be lucky with having guessed the b star. And we're lucky there with probability 1 over d minus n, d minus 1. So then we're done. If A wins and this stuff happens, then we get our X, and then we win our inverting game. And this happens with probability at least this, which is not huge, but it's fine. So then you can just play around with the probabilities and make everything work as we did in the lecture. So overall, for these probability analysis, you need to be lucky up here. So this should not happen. And you need to be lucky down here. So this should happen. I guess to be more precise, I should also say that not only should A win here, but also we shouldn't have bad luck here. Then we can do this whole analysis stuff, which I did say, I just didn't write it down. Good. Now the interesting thing here is actually that in the lecture you've seen the same equation here. Just that in the lecture it was d equal to 2. So this part, so this term here just vanished. It was just 1. And this kind of makes sense, right? Because in the lecture you had just bits to work with. So this event here didn't happen. So if mi star hat is not equal to b star, then we already know that mi star hat must be the other bit value. So it's a bit and it isn't b star, so it's the other bit. It's not b star. So let's say the adversary queried for mi star hat being 0. Then we already know that we were lucky here. So we know that mi star hat, this was not our b star, which means that b star was equal to 1 in our case. And then because mi star without the hat is not equal to mi star hat, we immediately get, because mi star hat is 0, then mi star needs to be 1. And then that's it. So in the lecture, we didn't even have to look at the probability of how likely is it that our b star is now the guess if we didn't had to abort in the first place. So if we weren't unlucky up here, we just know that just knew that we had to be lucky. But now that we have multiple digits, we still need to hit the right one where we have embedded our f of x. Okay, this was the overview for a generalized version of the Lamport signature scheme. Thank you for listening, and we'll see you.